Most of the galaxies appear to be moving away from us. Because the spectral lines are shifted toward the red end of the galaxy spectra as if they were receding, the visible universe seems to be expanding. According to one theory, a gigantic explosion occurred when the matter forming the universe had gathered into one cosmic mass billions of years ago. The galaxies, which formed from the exploded material, have continued traveling outward, farther and farther apart from each other, with the galaxies farthest away moving out the fastest. The rate at which the universe is expanding is defined by the Hubble constant, a number which indicates how quickly a galaxy at any given distance is moving away from us. But if we know the rate of expansion, we can calculate backwards to determine how long ago the galaxies in the universe were all together. That is, how long ago the universe began to expand. The present value for the Hubble constant places the age of the universe at just under 20 billion years, which is safely older than the oldest stars we can find.
What Hubble, Humason, and Slidell discovered is interesting and amazing. They found that the more distant galaxies have larger redshifts than the nearer galaxies. Now, the most common explanation for a redshift is motion. Motion, in this case, of the galaxy away from us here on the Earth. That motion causes the Doppler effect. And what this means, then, is that the farther away a galaxy is, the redder its light is, and the redder its light is, the larger its redshift. And the larger its redshift, the faster it's moving away. So the distant galaxies are going away from us at the fastest speeds. And in fact, all of the galaxies are moving away, and their speeds are directly proportional to their distances. Well, how do we explain all this? The simplest explanation is just that the universe overall is expanding. It's just getting bigger. And it's expanding uniformly, without twisting, without changing shape. All of the galaxies are getting farther away from all of the other galaxies. And from any particular galaxy, the Milky Way galaxy in which we reside, for example, it looks as though everything else is going away from us. Well, there's no reason for us to conclude that the rest of the universe doesn't like us. The rest of the universe sees exactly the same picture. Everything in the universe is moving away from everything else. Well, it's a short jump from the idea that the universe is expanding to the proposition that all this expansion began after a brief moment billions of years ago when the universe, the whole universe, was much smaller and much more condensed. Following an intense flare of light and heat, that expansion began, and as it did, the universe started growing larger and cooler and thinner and continued to the present state in which we find it today. Well, this picture, this idea of the expanding universe and its starting at this point is the so-called Big Bang theory of the universe. And of course, it describes a universe that is evolving. As the universe grows, it changes. And so the universe that we see today is different from the universe of billions of years ago. And of course, the universe of billions of years in the future is going to be different from the universe that we see now. Well, these universes that we talk about so glibly, of course, are really just interpretations of what we see in the galaxies and the light they send us. The Big Bang and the expanding universe itself are just interpretations of the data that Hubble collected. It's the most favored interpretation, of course, today, but still it's just an interpretation. And there was a problem with it when Hubble first proposed it, because his observations showed that the rate of expansion of the universe was really too fast. All of the galaxies were moving away from all of the others much too quickly. That rate of expansion actually implied an age of the universe that was too young, younger than some of the very objects in the universe. Well, this made no sense at all. And so, of course, it prompted some researchers to seek alternative explanations. And shortly after World War II, a competing theory for the expanding universe emerged, the so-called steady-state theory of the universe.
A steady-state universe was at one time a very attractive alternative to a Big Bang universe because the age of the universe that we deduce from the expansion of these galaxies has changed. I mean, our estimate of this age has changed by a factor of 10 since Hubble first tried to measure it. And at the time he tried to measure it, the age came out much too short for what we knew to be the age of the solar system by dating the radioactive material in the Earth's crust and so on. And it was too short by a large factor. And so it seemed that you couldn't, that in some way the universe must be older than it seemed from its expansion. And it turns out that the general relativistic equations, if you put a small extra term in those, then there's an alternate solution possible, which says that the universe has existed the same in time as well as in space. And this was the basis for the idea of a steady-state universe.
In 1948, Fred Hoyle developed his steady-state model of the universe, incorporating the original research of Hermann Bondi and Thomas Gold. The steady-state theory is based upon the perfect cosmological principle. Not only does the universe appear to be the same to all observers, but it looks the same at all times. The steady-state model also depends upon a process of continuous creation. There is no singularity or primordial atom, no distinct beginning, and no end. The universe has always been expanding, is expanding, and will continue to expand. The galaxies are created, live out their lifetimes, and disappear. However, the average density of matter in the universe always remains constant, rather than thinning out with the expansion, because it's assumed that new matter in the form of hydrogen is continuously being created and giving birth to new galaxies. Also, because new galaxies are forever being formed to keep pace with the expansion, the average separation in distance between them remains virtually unchanged as time passes. So, while the evolving, or Big Bang cosmology, contends that the matter in the universe is in fact thinning out, the steady-state theory contends that the density of matter is unchanging, and that dying galaxies are perpetually being replaced by new galaxies, formed from an infinite source of new hydrogen.
Well, from the point of view of theory, either idea could be correct, the Big Bang or the steady state. But here's where science really comes in, because we compare our observations to what the theory predicts, and we can tell that the steady state in its original form is not correct. The observational evidence discounts it. We see evolution in the universe, and we shouldn't see that in a steady state universe. According to the steady state universe theory, galaxies of different ages should be around us, young ones and old ones and some in the middle. But it looks to us like almost all of the galaxies are really of the same age, were formed at more or less the same time. And if we look far out into space, we're also looking very far back into time. And far back in time, things look different than they do now. For one thing, we see a higher concentration of radio sources in the past. And the quasars, too, seem to have been more populous in the younger days of the universe. But the real clincher came in 1965 with the accidental discovery of the remnants of the radiation left over from the primordial fireball, the Big Bang itself.
Now the question is, what happened to all of that radiation that was floating about in there?